All right, this is the Unit 6 test. So for number 1, what is the function that represents the exponential function y equals 70x? After a vertical stretch by a factor of 5 and a vertical shift up 2. Okay, so again, we're just thinking about this thing in terms of y equals a times b to the x minus h plus k. So here we've got a vertical stretch by a factor of 5. That goes in for the a. B is going to be 7 because we already have 7 over here. So they already give us the 7. So we just have to remember we don't change that. And then the last thing to decide is what to do with this 2. So this is a vertical shift, which means it's going to go in for the k. So k is going to be 2, which means that h is going to be 0 because they don't tell us anything about a horizontal shift. So that means all we got to do is plug in the x here and then 2 for k, and then that's it. So there we go. And we're done. So that's what we got. Again, if we want to double check it, we could double check it on graphing calculator or Desmos. But this one's just translations and transformations. So for number 2, we're given a function. It models population of butterflies after X years. What will the population be in 9 years? So here we're given a number of years, and we're going to plop that in for the X. So we'll get 5,100. 1.065. So again, we have growth. So I'm expecting a number that's bigger than 5,100 to the 9th power. And we just throw this into a calculator and then basically just call it a day. Oops, that's my video from before. So we get y 5,100, 1.065 to the 9th power. 8989. Right? Seems good. I got my numbers right. All right, 8989 it is. And again, if we're just talking about real world with the butterflies, 9,000, about 9,000 butterflies. All right, for number 3, we got our function. We have to identify our 4 same domain or 4 same pieces that we did on the quiz: domain, range, y-intercept, and asymptote. Again, it's an exponential function. So for an exponential function, the domain is always negative infinity to infinity. So we can knock that out. For the range, again, this time we have a little bit of a difference here because we have this minus 3. So we know we're going to have something a little bit stranger. So that means we're either going to go from negative 3 to infinity or from negative infinity to negative 3. Now, since we have the negative sign here, we're going to end up going from negative infinity to negative 3. The asymptote would be at y equals negative 3. And lastly, the y-intercept. For the y-intercept, we're going to take this number that we have, but this time we have to be careful because we are shifting down by 3. So we'd normally be at negative 2, but now we should be at negative 5. And if we want, we can double check. Negative 2.5 to the 0 minus 3. Negative 2 minus 3 is negative 5. Now, this is going to throw you, if you feel this is going to throw you a little bit, I would say try it out. So let's plug it into Desmos. Let's plug it into a graphing calculator and see what we get. Negative 2.5 to the x minus 3. And we can see, all right, yeah, I got the y-intercept, 0, negative 5. Looks like I'm tapering off here. We're headed towards negative 3. Remember, it's not exactly negative 3. That's just rounding for Desmos. And we're going down to negative infinity. All right, I feel pretty confident with that. I feel pretty good with all those ones. For number 4, what's the equation of the exponential model in the form y equals a times b to the x? Passes through the points 1, 8 and 2, comma 32. So a couple ways to do this one. There is a formula for it. We can actually find out what b is. B is going to be x2 minus x1th root of y2 divided by y1. So you might remember that one. We did a little bit of practice with that in Algebra 1. Not too much because it is a really complicated formula. But if we do that, it's going to be 2 minus 1 root of 32 over 8. So that means we're going to do 32 over 8. The first root of 4 is just going to be 4. So we can tell that b is going to be 4. 4 to the x. And now we can just pick any point that we want as x and y. I'm going to pick this one. So I want 8 equals a 4 to the first power. So that means that 8 equals 4a. Divide both sides by 4. 2 equals a. And I get my final equation, y equals 2, 4 to the x. And that's it. So that's what I can do. So I can use the equation and a point if I wanted to do it all by hand. Since we are given 2 points, we can try. This isn't always going to work if you have 2 points because you really want to have 3 points, but we could try doing a regression. We'll see. We'll see if it yells at us or not. We're going from 1, 8 to 232. I'll turn that off. Y1 tilde a b x, because we want that to be the equation that we have. And yeah, it gives us the same answer. So that's kind of interesting. Again, with 2 points, sometimes it doesn't work. Let me get both points on screen. 2 points, sometimes it doesn't work, but in this case it did. We did get a equals 2, b equals 4, which is what I've got here. A equals 2, b equals 4. So that's what we got. So again, this whole thing with the b, this is if we're given 2 points that are kind of wildly away from each other. We could also notice that, hey, we're going up by 1 and we're multiplying by 4. So we know that 4 is going to be b. That would be a logical way to do it. But let's say you didn't want to do it the logical way. Let's say you want to do it all algebraically. There is the formula. You can use this formula for it. So that's number 4. All right. For number 5, what's the average rate of change from 0 to 4? Again, average rate of change is going to be the slope. So what we're trying to find out is we're trying to find out the slope. So since I got the picture, I'm just going to do rise over run. Oh, I don't know what happened there. So if you want, you can do y2 minus y1 over x2 minus x1, f of b minus f of a over b minus a. But again, I'm given a picture. I'm just going to count 1, 2, 3, down 3, 1, 2, 3, 4, over 4. And I'm going to call it a day at negative 3/4. So that's it. That's all there is. All right. For number 6, we have a warren of rabbits with a population of only 40 rabbits, but the population is increasing at a rate of 18% per year. How can we write an exponential growth function to find the monthly growth rate? All right. So here we need to find the monthly growth rate. So we're going to use the big equation, y equals a, 1 plus r over n over nt, or to the nt power. A is the number of rabbits we've got at the start. That's going to be 40. 1 plus r. Well, r in this case is 18%. So 0.18. And we need to do the monthly growth rate. So monthly means n is going to equal 12. So over 12 equals, or to the 12t power. This is equal to y, and that's it. So we just had to get the growth rate. My 12 doesn't look like a very nice 12, so I'm going to fix that. I don't know, it kind of looks like an R to me. So 12t. All right, there we go. And that's it. That's all we want to do is just write the exponential growth function. So that's what we want to do for growth. I forgot to say, since it is growth, that's what dictates this being a plus sign instead of a minus sign. So if it's decay, that would be a minus sign, but it's growth, so that's going to be a plus sign. All right. For 7, what's the inverse function and inverse of the exponential function y equals 9 to the x? So to find the inverse, we switch the x and the y. So I'm going to write that as 9 to the y equals x, and try and get the y by itself. Make a nice little snail. So we get 9, oops, already have a 9, log base 9 of x equals y. And that's it. We're done. Again, if you want, you could, when we get to this step, you could say that I'm going to log base 9 both sides. Because remember, log base 9 of 9 is going to become 1. log base 9 of x. But we need to use our property where our exponent can become a coefficient. Log 9 of 9, and then this is equal to 1. And so then you'll get to the same answer, log base 9 of x equals y. So you get the same thing. So you can do it either way, whatever you like better. For 8, evaluate the log expressions to 4 decimal points if necessary. This is just straight calculator work. The reason it's straight calculator work is, all right, yeah, the first one, you can just tell it's 1 because, again, you have what we are taking the log base of and what we have inside here. Since these are the same, the answer is going to be 1. With log base 2 of 32, if we want to do this one by hand, what we would do is say, okay, well, we'll make that equal to y. So 2 to the y equals 32. And we just have to think about this logically. Okay, y has to be 5 because 2 to the 5th is 32. All right, makes sense. But the reason this is just a calculator question is because of part C. We don't really know log of 15. We just have to type that into a calculator. So that's all we got. Just remember this is log base 10. But when you use a calculator, you don't have to put the little 10 underneath there. 1.1761. That's it. So a little disappointing. It is just a straight calculator question. And since part C requires a calculator, you're more than welcome to put parts A and B both into the calculator as well. You don't need to, but you could if you wanted to. All right, for part 9, what's the solution to the equation log base 3 of 2x plus 1 equals 2? Again, we're just going to go ahead and make a nice little snail here. Say 3 to the 2nd equals 2x plus 1. So that means 9 is equal to 2x plus 1. Subtract 1 both sides. 8 is equal to 2x. Divide by 2. 4 is equal to x. All right, all set. Seems pretty good. We can double check it. We can plug it back in, so we could double check it by hand if we wanted to. So log base 3 of 2 times 4 plus 1. Log base 3 of 9. And yeah, 3 to the 2nd power is 9, so 2 equals 2, check. If we wanted to check it by graphing it, we could also do that. So we can also check it that way. So we want log base 3. This is in the calculus section for some reason, but that's where it's at. Log base 3, 2x plus 1. And we want that to equal 2. So y equals 2. Let's turn this off so we don't get confused. And let's go home. And we get 4 as our answer. So yeah, the graph matches up also. So the graph tells us x is 4 is the answer. We're all good. So everything looks pretty good there. For 10, we have to find the inverse function f negative 1 at x equals 8 for our graph here. I'm kind of in the way of the other point, negative 1, 2. But the cool thing is that does not matter whatsoever. The only thing that matters is we're doing an inverse. So guess what? We can just flip these. So for the inverse, if x equals 8, y equals 1. So we're done. That's it. That's all it is. If you want, you can go through the whole process of finding the inverse function, but they gave us that point. And the reason that they gave us that point was to use the definition of an inverse. So that's it. That's all you got to do. If you do want to do it by hand, again, this is like y, that's like x. So we would say x is equal to 4, 2 to the y, divide both sides by 4. So we have to be really careful here. I can't divide by 8 because remember, this is exponents first. So order of operations, but not allowed to multiply this 4 in with the 2. And then I would have to do log 2 of both sides. Or you could snail it. So we get log base 2 of x over 4 equals y. And now is where we plug in x equals 8. So we have log base 2 of 8 over 4 equals y, which is log base 2 of 2 equals y. And this is our favorite property where we're doing log base 2 of 2. So this is going to be equal to 1. So we get 1 equals y. So we can get it the same way. Again, they gave us the point on the graph specifically to shortcut it. But if you need to go the long way, that's the long way to do it. So that's how you can do it. The other way to do it, I guess if you're given the function but not given the graph, is to make a graph out of it. So if we had 4 times 2 to the x, let's take these ones away. So this is kind of cool. 4 times 2 x. If I want to find the value at x equals 8, I just need to find out where I connect it with at y equals 8. And so I'm at 1. So if I want to know what it would be if the inverse was x equals 16, it would be 2, because that's where they would connect. So that's kind of cool, because again, you just flip-flop your x's and y's. But for this case, probably all much more complicated than saying, oh, I have 1, 8, so I also have 8, 1 on the inverse, because I'm going to flip them for the inverse. Let me make this table super clear that that is the inverse. Even though it's all in blue, this is f to the minus, not f prime. That's why it's in the calculus section, obviously. F inverse of x. That's a little table for that. So that's what we got for 10. For 11, we have the logarithmic function f of x ln of x is transformed to ln of x plus 4 minus 2. Describe the transformation of f of x to g of x. So we can see inside here we have minus 4 plus 4, which means we're going to the left 4. Outside the parentheses, minus 2 means down 2. And just like everything else we've done with the a's, h's, and k's, that's the end of the question. So that's all we got. So again, that's one of those transform questions. If you're unsure, you can always graph it and double check. So you can graph ln of x, ln of quantity x plus 4, and then minus 2. But it is a's, h, and k's. H is 4, left 4. K is negative 2, down 2. For 12, find the equation for the inverse. F of x is log of 4x. So this one, kind of like we did in number 10, we actually have to find the equation now. So y equals log of 4x. So I'm going to write this as log base 10 of 4x equals y, which lets me go ahead and do this. Oops, can't do that yet. Oh, I forgot. Undo. I got to switch my x's and my y's. I forgot to do that at first. Let's do that at this step. So we'll switch the x's and the y's because we want the inverse. So that's going to be the y, that's going to be the x. So now when we do this, it makes more sense because now we're actually starting to get the y by itself. 4y equals 10 to the x. And so this 10 to the x is going to be the part that most people are going to mix up because there's no base 10 here, even though it's implied. And now this time we're dividing by 4 afterwards because the 4 was inside instead of outside the parentheses. So y equals 10 to the x over 4. And that's the answer. So it's not going to be 2.5 to the x. We don't divide those because remember, we have to do exponents first. It's 10 to the x over 4. And that's it. So that's our equation for y. Let me write it with the inverse notation. F minus 1 of x is equal to 10 to the x over 4. There we go. All right, for 13, expand the expression. So we're going to use our properties of logarithms in order to expand this. So what we want to say is when we're expanding, we kind of have a good order to do things. So the first thing we want to do is do any do any divisions to subtractions. So divide to subtract. So that's step 1. So that means we're going to turn this then into ln of x squared y minus ln of z to the third. And again, that's because we're dividing by z to the third. So I'm turning my division into a subtraction. Step 2, usually then you want to turn the multiplications, that's how I spell multiply, into additions. So at this point, we have an x squared times a y. So we're going to have ln of x squared plus ln of y, and then still minus ln of z to the third. That didn't really change. And then the last step, when we do these, usually is going to be any exponents are going to become coefficients. So that means this 2 is going to hop out front. So we'll have 2 ln of x. Y doesn't really have an exponent. I mean, it does of 1, but I don't really need to write that. So ln of y. And this cubed for the z, the 3 is going to pop out front. And that's what we got. So now we're totally expanded. And the reason that we want to expand it is maybe we want to be able to change x, y, and z like on their own and keep the other two the same. So let's say we wanted to do a bunch of calculations where we knew x and y, and we just wanted to change z. Well, now we just have this one piece. This would just be a number minus 3 ln z. So it would be a little bit faster to do the calculations. So that's expanded. All right. 14 is the reverse. We're going to condense. So we're just going to make one logarithm out of all this. So we're literally going to do all of our steps we did here just in reverse. So we're going to turn coefficients into exponents. So that's going to be our first step. So here I've got a 3, I've got a 4, and I've got a 2. So we're going to go ahead and do log 2 to the third power plus log a to the fourth power minus log b to the second power. All right. Well, now we're going to change. I forget what color I picked. Adding to multiplying. So that's going to be in red. So add. Oops. So here I can see I'm adding. So we're going to turn this into log 2 to the third power, a to the fourth power, minus log b to the second power. And lastly, did I pick purple last time? I picked black. All right. So to finish up our reversal, we're going to turn any subtraction into division. So here I've got a subtraction, so I'm going to turn that into division. So we're going to get log 2 to the third, a to the fourth, b squared. Now when we condense, there's actually going to be one last step. There is a simplify step at the end. So sometimes things will cancel out. In this case, nothing's going to cancel out. But I can figure out what 2 to the third is. So that'll just be 8a to the fourth, b to the second. So that's going to be my fourth step. Again, it's just nice so that we turn 2 to the third in one number. It just makes it a little bit easier. So that's what we got for number 14. All right, for 15, we have to solve this equation for x. First thing says, give an exact solution as a logarithm. Okay, well, I'm going to log 4 both sides. So log base 4 of 11. All right, approximate the solution to the nearest thousandth. All right, I can just type that in now. Let's see. Let's use, I'll just type it. So we're going to do log base 4 of 11. Log base 4 of 11 is 1.7297. Nearest thousandth, so 3 decimals, 1.730. Good. And that's it. All done. All right, so I think that's a little bit weird. Like, why is that part A and part B? Well, the reason that it's part A and part B is because if I really wanted to answer the question, 4 to the x and 11, I could just solve it by graphing. I didn't want you to solve it by graphing, so made you actually do the algebra first, and then you can solve it by graphing and get the answer this way, or you can get the answer just by typing it in. So either way. But that's why it might look a little bit strange to have a part A and part B there. Same deal here. So we're doing the same thing. Since I did the snail method, the other one, for this one I'll do the other method. So we want to take the log base 5 of both sides. Because log base 5 of 5 is 1. So we get x equals log base 5 of 2. So that would be our exact solution. Approximate the solution to the nearest thousandth. Same deal though. So we're just going to change this to log base 5. Oh, everything got all messed up. All right. Log base 5 of 2. 0.431. There we go. So that's all we got for that one. Pretty much the same as the other one, just an extra example. For 17, solve the equation by using a common base. So if they want us to use a common base, let's go for it then. So we know that 9 is going to be 3 squared. So we got 3 to the second to the x minus 2 equals 3 to the x plus 2. Power to a power means I get to multiply. So that means I'm going to have 3 to the 2x minus 4 equals 3 to the x plus 2. And now what we want to do is we want to take log 3 of both sides. The reason for that is log 3 of 3. I don't want to there. Ooh, I got rid of everything. Log 3 of 3, remember, that's just going to be 1. So these ones are actually going to go away. Now, you might remember back in like 7th or 8th grade, you can just cancel these 3's out because if the bases are the same, you need the exponents to be the same. So you can also use that rule. All right. So like I said, we're going to get this. Cancel these out. So we'll get 2x minus 4 equals x plus 2. And then we have to solve to get x by itself. So we subtract x from both sides. So we get x minus 4 equals 2. Add 4 to both sides. So x equals 6. All right, so it seems like we're pretty good. We do want to double check it just to make sure it works out okay. So 9 to the 6 minus 2 equals 3 to the 6 plus 2. So this is what we're checking. So we have to see if 9 to the 4th power is actually equal to 3 to the 8th power. Now, since we are checking, I could just say, yeah, it's true because I know it's true. But since we're checking, we may as well plug them in. 9 to the 4th, 3 to the 8th, and see, okay, yep, 65, 61 equals 65, 61. So that's one way to check it. Again, it's an equation, so you do have the option of checking it by graphing. So we can check it by graphing. So let's go for it. 9 to the x minus 2. X minus 2. 3 to the x plus 2. All right, let's turn off y equals 11. We don't want that. We also don't want 4 to the x. And I have to find out where these two things connect. So you can see why solving this one by graphing may not be optimal. Because those things, I don't even think they've connected yet. No, I don't see any gray dots. Are they connecting yet? Nope, I still don't see any gray dots. Oh, there it is. Oh, okay, yeah, it is at 6. So you can see we had to zoom out way high way because those are going to connect at a very high y value. So not really the optimal way to solve this one is to solve by graphing. You can check by graphing, but if you notice the question says solve it by using a common base. So if you don't use a common base, you did not actually answer the question. So you need to get these to have the same base. In this case, they both have to have this base of 3. And then once you get down to this equation, then you're pretty good to go. So that's what we got for number 17. For number 18, find all solutions to the equation ln of x plus 2 equals 2 ln of x. Label extraneous solutions. So again, this label extraneous solutions right here makes it so that you can't just solve it by graphing. Because if you solve it by graphing, you aren't going to get any extraneous solutions. Extraneous solutions will not pop up. So what you need to do is take this 2, and you need to actually condense this. So this 2 is going to go back over here and become an exponent for x. So ln of x plus 2 equals ln of x squared. Now that these are both ln's, if we want, we can raise both sides to the e power, because e to the ln would be 1. They would cancel each other out. They're inverse operations. So we get x plus 2 equals x squared. And now I see I have an x squared equation, so I solve this like we did in Unit 2. We'll throw everything on the same side, so 0 equals x squared minus x minus 2. So 0 equals, multiplies to negative 2, adds to negative 1, x minus 2, x plus 1, x equals 2, x equals negative 1. So these are my two solutions. They could both be extraneous. One could be extraneous, or neither could be extraneous. We aren't quite sure, so we actually have to check them out. So when we plug them in, ln of 2 plus 2 equals 2 ln of 2. So we get ln of 4 equals 2 ln of 2. So that's something that we'll probably have to check. We really don't have to. We could put the 2 back in there and it'll work out. But just for checking's sake, ln of 4, 2 ln of 2, and yeah, those are the same. So those work out. So I like that one. That one's pretty good. This one's all good. All right, we try out -1. So ln of -1 plus 2 equals 2 ln of -1. And right away we can see you're not allowed to put a negative in the logarithms. So we can't put that negative inside the ln, so this one is extraneous. So we don't want to pick this one, but we do need to label it as an extraneous solution because that's what the instructions tell us to do. So that also prevents you from actually solving this totally by graphing. Again, I'm making you actually do the algebra here. You cannot solve that one just by graphing it and finding where they cross. They will cross at 2. They will not cross at -1. We can double check it if we want to double check it. ln x plus 2. Let's get rid of these ones. And 2 ln of x. See, yep, okay, they definitely cross here at 2. But you can see the green one, and this is why we said that it didn't work, is that that green one never gets to -1. X equals -1 is outside of its domain. So we don't actually pick that one. All right, for number 19, okay, now this one tells us explicitly to solve it by graphing. So let's just go ahead and solve it by graphing. So log base 3 of 2x equals x. All right. Log base 3. Oops, I missed my little base. I kind of forget what that was. I want to say it was 2x. Let's see what it actually was. Log base 3 of 2x equals x. Okay, sounds good. Well, we have an issue now because we have to find where these things connect, and it does not appear that they connect. Let's zoom out a little bit just to double check. I guess that's some black dots from before. Let's turn those off. Yeah, I mean, we can zoom out. It looks like they cross, but that's only because we zoomed out a lot. Because remember, we zoomed back in, and they don't actually touch. Okay, well, no solution. If they don't actually touch, no solution. All right, well, again, I guess that's it. I guess we're done. All right. So for number 20, what is the solution to this equation? Is this the last one? This is the last one. So let's go ahead and solve this one. So if I'm looking at this, I kind of got 2 options. My first option is to take log base 3 of both sides or log base 2 of both sides. If I have to choose, I think I'm going to do log base 3 of both sides. The reason for that, oops, my log base 3 in here, is remember, now that these are exponents, I can turn them into coefficients. So x log base 3 of 2. Now, remember, log base 3 of 3 is going to be 1. So what this did is I got x minus 1 to be by itself. I think that's going to be more useful than just getting this x to be by itself. Because that way I only have one term that's got that weird log base 3 of 2 with it. If I did it the other way, if I chose the log base 2, then I'd have to deal with the log base 2 with the x and with the 1. So I think this is going to be the most useful way to do this. So I need to get x by itself. So what I want to do is subtract x on both sides. So we're going to put all the x's on one side, and that's pretty normal. So we usually do that when we try to solve equations. We get all the x's on one side. But here, since these both have x, I want to do a greatest common factor of x. So since these both have x with them, I'm going to do x, and this one, if I divide it by x, I'm going to have log base 3 of 2. If I divide this one by x, I'm going to have 1. And now to get the x by itself, it's actually really easy. I just divide by this giant piece of junk that I have right here. So that's actually not too bad. Negative 1 over log base 3 of 2 minus 1 equals x. Is it pretty? Well, I think it is. I think that looks very nice. You might not think that looks very pretty. And you might think, all right, well, we'll just throw it into the calculator now, and we'll see what that actually is. Negative 1 over log base 3 of 2 minus 1. 2.07, 2.7095. Where do we have to go to? Oh, it doesn't even say round to anything. So this is about 2.0795. I think I messed that up. 7095. Let's just do 71. 2.71 is a fun number. So it's about 2.71. All right. Seems pretty reasonable. Looks like we got it. If we want, we can double check it. We could plug it in just to double check to make sure it works. We don't really need to in this case because these are both exponentials, and exponentials have a domain from negative infinity to infinity, so we're not going to get caught out like we do with the logs. So that's my solution. If I want, I can double check it by graphing. If I want to graph this one, I am allowed to double check this one by graphing. There's no rule that says I can't double check it. So let's see what we got. If we do 3 x minus 1 and 2 x. All right, 2.71. Looks like we got it. All right, pretty good. So pretty nice that we can double check that one too by graphing if we need to. Well, that's what we got. So all we're gonna do is nice little log exponential inverse operations. So that's it. That's everything with the Unit 6 test. So again, some of the questions went by pretty fast. This one's not a very long one, but hopefully we'll do pretty good with this one. So that's it.